Hello, everyone. I'm Elisa. I'm a PhD student at a German university, but I'm doing part of my research at Polytechnique in Montreal. And my research is mostly focused on shallow geothermal energy. And today I would like to present some results from the work at Polytechnique. And it's about reconstructing thermal response functions from monitoring data. To get into the topic, I first want to explain what thermal response functions actually are and why we need them. They are also called G functions, and they are basically dimensionless functions of time that describe the heat exchange capacity of ground heat exchangers in response to a unit impulse signal. And ground heat exchangers can be any type of heat exchange system in the subsurface, such as, for example, borehole heat exchangers or collectors, but also open loop systems. But in the following, I will mostly talk about borehole heat exchangers. Here we can see an example of a thermal response function. So it's a function of time. Here it's logarithmic. And this G value describes the heat exchange capacity of one borehole in this case. And we can see that in the beginning, the curve increases linearly, which means that heat transfer takes mostly place in radial direction. But at some point with longer time, it reaches this plateau. And this means that the borehole operates in steady state mode. Then back to the unit impulse signal. This can be, for example, 1 watt of energy extraction from a borehole, but also 1 Kelvin of fluid temperature difference between the water entering and leaving the borehole. And as an example, here you can see the energy demand as heat extraction rate in watts from a building over 1 year. So there's a heating demand in the winter months and a cooling demand in summer. And now the interesting thing about those thermal response functions is that by convolution of this function, which is characteristic for this one borehole in this case, and the energy demand, and that's what this convolution operator here stands for. I will explain that later. It's possible to predict the fluid temperature that comes from the borehole or from the ground heat exchanger system. And this is very practical because this convolution operation is super fast and efficient. So we can make predictions of the fluid temperature for several years. And that's the reason why those G functions are commonly used for the simulation of ground heat exchange systems. Okay, so how can we obtain those G functions? The most common approach to obtain them are the most commonly used G functions are the ones that were created by Eskilsson in 1987, who simulated the borehole wall temperature of different borehole field configurations using a numerical model. And this way he published a catalog of different G functions specific for borehole field configurations. The G functions by Eskilsson are only valid for longer time steps and cannot be used for time steps below a couple of hours. But any physical model can be used to obtain those functions. And in recent years, there have also been methods published to obtain short-term G functions. The problem with all those G functions obtained from physical models is that they are all bound to the simplifications that are made by the physical model. And this is why a very recent approach to obtain G functions that circumvents those simplifications is to obtain them directly from the experimental data using deconvolution. And the experimental data is usually data from thermal response tests on geothermal systems. And this way it's possible to obtain experimental G functions. And the advantage of those functions is that they incorporate all heat transfer processes that take place in the subsurface and are independent on a physical model. But since this deconvolution part is very new, it has so far only been applied to data from thermal response tests and only to data of several days. So what I want to present today is an application of this deconvolution algorithm to monitoring data of a borehole heat exchanger field with 40 boreholes and for a duration of 30 days, so 1 month. And for this, I first want to present a borehole heat exchanger field where I applied this algorithm to. and a monitoring system. So here we can see again the building that was already on the title slide. It's our university building located in Aachen in Germany, and it has offices, laboratories, and server rooms. It was built in 2011, and to cover parts of its energy demand, it's equipped with a field of 41 borehole heat exchangers that are shown here as those gray circles and numbered. They are all double U-tube borehole heat exchangers and 100 meters deep, and installed in a geological environment that's mostly dominated by unconsolidated sediments, silt sand, clay, and some coal fragments. To connect all those individual boreholes to the building, they are assembled in 3 manifolds or shafts. That's what those little gray boxes are for. And in each of those shafts or manifolds, there are sensors placed. So each borehole has a BELIMO valve, that's this orange thing, and sensors for the inflow temperature going into the borehole, the outflow temperature, and also the volume flow. And this data is recorded in 30-second intervals and streamed to a cloud platform from which it can be visualized and inspected for further analysis. And this data is available from 2011 up to now, so it's a huge data set. And as an example to show you how the data looks like, here we can see the data of borehole number 18. It's from the beginning of this year, from February until the end of May. And in blue, we have the inflow temperature and the outflow temperature corresponding to the left axis. And in gray, we see the flow rate of the borehole corresponding to the right axis on this plot. And we can see that even though it was still in winter, the field was used for cooling, which we can see because the outlet temperature is lower than the inlet temperature. And this is a very good data period because there's no data missing. And in this area here, we have a relatively high temperature difference between the inlet and the outlet, and also a constant flow rate, meaning stationary conditions. So this is the data period we used to reconstruct the G functions of each of the boreholes. Now I want to briefly explain how those G functions can be obtained from the data. And for this, I will explain the deconvolution algorithm that was developed by a colleague at Polytechnique. This is the equation we already saw in the beginning. So the fluid temperature leaving a borehole as a function of time can be expressed by convolution of an excitation function F and a G function G. And convolution is a mathematical operation on 2 functions, F and G, which creates this third function that describes how the shape of one function is modified by the other function. In this equation, T is the temperature variation at the borehole outlet, and it can be obtained from the monitoring data from the fluid temperatures, which is shown here in this plot. F, the excitation function, is in this case the incremental temperature function. It's also obtained from the temperature measurements in this period by taking the first derivative of the temperature difference between inlet and outlet. And then from this, the missing piece, G, the G function, can be obtained by a process called multi-objective constraint iterative optimization. And this basically creates a strictly monotonic function to find the G that best fits into this equation by minimizing for minimal error in respect to T. And this way we obtain this experimental G function here. That describes the heat exchange process of the borehole in this period. And we applied this algorithm to data of all the 41 boreholes. Then we can also go back in this equation here and assuming we don't know the temperature variation and obtain a convolution product of this experimental G function in F. And this way we obtain the deconvolved temperature signal, which we can compare to the measured signal, for example, using an error metric such as the root mean squared error. And this we applied to data from all the 41 boreholes, and this way we obtain the G function of each individual borehole here. And those functions is what I'm going to show here. So here we can see the G functions for the western, southern, and eastern manifold. So each of those lines represents one borehole. And we can see that the functions have some things in common, but there are also some differences. So what they have in common is that they are all linearly increasing and relatively smooth. But they show differences in terms of how G increases here. And thereby, the more G increases, the worse is the heat exchange capacity of the borehole. So in this western shaft, the blue lines, there are 2 boreholes that have a worse heat exchange capacity than the other ones down there, which correspond more to the G functions from the southern manifold. Yeah, so those G functions show differences in the heat exchange capacity of the individual boreholes. Yeah, so how well do those G functions describe the outlet temperature of the boreholes? For that, here we can see the root mean squared error between the measured and the deconvolved temperature signal as a color code of the individual boreholes. And we can see that the root mean square error is for all boreholes below 0.09, which means that the temperature of those G functions can be well reconstructed. Okay, so to sum up, we have seen that it's possible to obtain experimental G functions from monitoring data for a period of 30 days. And this opens up a range of possibilities. For example, those G functions can be used for the long-term analysis of borehole fields, and also to analyze changes in the heat exchange capacity over time. The big advantage of those functions is that they incorporate all heat exchange processes that take place in the subsurface and are independent on a physical model. So they can be used for subsurface parameter estimation and also to optimize the operation of ground heat exchange systems. And last but not least, we have seen that there are some differences in the heat exchange capacity of the boreholes. And this is due to many different reasons. For example, the number of neighboring boreholes or the current temperature of the borehole. And analyzing this in more depth is one of my next steps. And with that, I want to thank you for your attention, and I'm happy to answer questions.